So from a reaction, we know how to write the equilibrium constant expression, but let's figure out how to get the values. So what we're going to do now is look at finding, by which I mean calculating, the KEQ from the equilibrium concentrations. So this is the most direct way to find the equilibrium constant, which is you get a reaction at equilibrium and then you measure the concentration or the pressure and plug in those values, right? The values at equilibrium are what we use for the equilibrium constant. So here's an example. At 445 degrees Celsius, the reaction H2 plus I2 in equilibrium with 2HI. If at equilibrium, my H2 concentration is 0.11 molar, my I2 concentration is 0.11 molar, and my HI concentration is 0.78 molar, my equilibrium constant, the expression for which is the concentration of HI squared divided by concentration of H2 times concentration of I2. And then I just plug in concentration of HI at equilibrium is 0.78. So 0.78 squared divided by 0.11 times 0.11. This gives a value of 50. So the equilibrium constant for this reaction at this temperature is 50. The equilibrium lies to the right. This means, right, this reaction, when it gets to equilibrium, has more product than reactant. Now, what's more likely is that we know the initial concentrations and then the equilibrium concentration of one component. Now, this is still 100% solvable. I think if I give you something that's not solvable, I've definitely made a mistake in setting up the equilibrium problem. So here, if we know where we start and we know some information about where we end, we can still do this exact thing, which is find the equilibrium concentrations or pressures, concentrations here, and then plug those values into the expression. So let's say for my reaction A in equilibrium with 2B, I initially have 1 molar A, no B, and at equilibrium, I have 0.75 molar A. And that's the only information I'm given. Now, often you might just be given that the initial values are that the concentration of A is 1 molar. And then if it doesn't say anything about B, it means that there's no B. And then at equilibrium, I have 0.75 molar A. So a couple of things going on here. We are going to treat concentrations kind of like they are mole values. This is only possible because all of my reaction is in the same size container. So it doesn't matter what the container is or if we're doing pressures or we're doing concentrations, because unless I have this perturbation of changing the size of the container, which we're only going to do one thing at a time, so we don't have that. If everything is in the same size container, the pressure and or the molarity is a proxy for the number of moles. So I don't have to go to the number of moles to do this calculation. I can just treat the concentrations that way. Now I'm giving you the why because there will be cases later where we have to go to moles and then we have to go back to concentration. So here we don't have to get out of concentration. Now, what we're looking at, if I know essentially how much of my A was used up, I can figure out how much B was made because I have a balanced reaction, right? I have coefficients that tell me the mole ratios of how these things react with each other. So at equilibrium, the concentration of B is 2 times however much A I lost. So my concentration of A went down by 0.25 molar. So my concentration of B has to be twice that because I have a 2 coefficient in front of it. So my concentration of B at equilibrium is 0.5 molar. Now, there is a better way to organize this. It's going to be in something called a rice table. You might have heard it called an ice table before. Um, it might feel like overkill for some of the problems that you do, but organizing things in a rice table, it may be extra, but I don't think it could ever be wrong unless you're just not dealing with an equilibrium. So rice is just, it stands for the row headers, titles, labels, the row labels. So it's going to be the reaction, the initial values, the change, and then the equilibrium at the bottom. So I have my reaction A in equilibrium with 2B. My initial conditions, which I'm given, I can fill in 1.0 and 0. And then I don't know, like I have to figure out the change row. In this case, what I'm given is that the equilibrium concentration for A is 0.75. So I also usually just draw a big line between the change and the equilibrium, because if you look at each column, the initial and then the way that it changed, we're just adding everything together in that column. So in my column under A, if it's initially 1.0 and at equilibrium it's 0.75, the way that it changed was that I subtracted 0.25. So I've filled in the 0.25 minus 0.25 here. Now, across the change row, everything is related through the mole ratios. So for every 1A that I use up, I make 2B. So if I'm using up A and I'm making B, and A is a minus, then B has to be a plus. And if it's 0.25A, then I had to make 0.5B. And now 0 plus 0.5 is 0.5. Those are my equilibrium values, 0.75 and 0.5. So when I plug them into my equilibrium constant expression, it would be 0.5 squared over 0.75, which is 0.33. So my equilibrium constant for this reaction is 0.33. Okay. One more example, a little bit longer, and I have put things in my ice table in order and, fancy color coded them so that you can see what's coming in when and then how to go between the steps. So carbon monoxide plus 2H2 gas in equilibrium with CH3OH. If you have a reaction mixture at 780 degrees C, it initially contains 0.5 molar carbon monoxide and 1 molar hydrogen gas. At equilibrium, the carbon monoxide is 0.15 molar. We've been asked to find the Kc. So, the C, great, concentrations. We have concentrations. Awesome. We don't have to do anything there. I'm going to set this up with a rice table. So I've got my row labels just with the capital letters, and I've got my reaction filled in. So the first thing, like with any problem solving, we'll fill in what we're given, which is the 0.5 molar initial carbon monoxide, the 1 molar initial hydrogen gas, and it doesn't say anything about the CH3OH, so I have 0 when I start of CH3OH. And the other piece of information I know is that at equilibrium, my carbon monoxide is down to 0.15 molar. So this is where I'm starting. The next step, I have it labeled as fill in EZC. So in the change row, there will be something where all of the other parts are set up for you. So under carbon monoxide, 0.5, blank spot, 0.15. So how does this have to change in order to go from 0.5 to 0.15? I lost 0.35 molar, so minus 0.35. That's it for the next step. Then you use stoichiometry for all of the other change values. So carbon monoxide, I lost 0.35. Hydrogen gas, also a reactant. So when I use up carbon monoxide, I also use up H2. So this is why it has a negative. But I use twice as much, right? That's what my coefficient tells me. So I'm going to lose 0.7 molar of H2. And then the CH3OH, it's a product. I'm going to make this, so my change is positive. And based on mole ratios, I'm going to make 0.35 of it. Once you have the change row in, you would complete the equilibrium row. So for CO, it was given. For H2, 1 minus 0.7 is 0.3. For CH3OH, 0 plus 0.35 is 0.35. And now I have all of the numbers I need to calculate my equilibrium constant. So it's CH3OH divided by CO times H2 squared. So 0.35 over 0.15 times 0.3 squared, and you get an equilibrium constant of 26.